Okay, so today, this is the title. I'm going to start with that. That is Zooming Quantum Mechanics Below Planck Scale. So when you talk about the quantum mechanics, then the Planck dimension becomes very important. And here actually I'll discuss about something which is dimension is below Planck scale. And one can see here, there is a nice picture also. So I'll explain what are those in my talk. So quantum technology, this is actually the new generation technology where a lot of work has been going on to develop this, and it has immense power to change our daily life also. So the first quantum revolution, it happened long before. It's early of 20th century when scientists developed the fundamental laws of quantum physics, where for that we have been using these semiconductors, transistors, GPS, atomic clocks. So all those things we have been already using in our life. But the second quantum evolution, I think we have already entered into it, because now we are not exploring these fundamental laws, but we are trying to control the individual quantum system. Okay, we can manipulate, we can engineer over there, and so we are now exploiting the properties like quantum superposition, quantum entanglement. So it has no any classical counterpart, and it opens a new window. So different kind of fields, for example, quantum sensing, quantum computing, quantum communication. So these are the fields are developing very rapidly, and it can together build this new technology, which is the quantum technology. Okay, so last year we have just crossed this year. This is the International Year of Quantum Science and Technology. So we celebrated the 100th anniversary of discovery of quantum mechanics. So let me start with this milestone very briefly. Uh, it's the end of 19th century when scientists thought that they can discover everything based on these three pillars. One is mechanics, another is electrodynamics, and the thermodynamics. But there was some problem with the explanation of blackbody radiation. And in 1900, Max Planck came with the revolutionary idea that this energy, it should be emitted, when emitted or absorbed, that should be in a discrete manner. So that is the idea of quantum. And he explained the blackbody radiation. Now, after 5 years, Einstein uh, explained the photoelectric effect, and he said that not only this light itself is quantized. Light itself, it's made of some particles which is called the photon, and he gave the explanation of photoelectric effect. And there are also some other problem at that time. There's the stability of atomic structure. So Rutherford did the experiment, and he mentioned about the nucleus and then gave the planetary model. But there was again some problem. As the charged particle will accelerate, then it will radiate energy and it falls on a nuclei. So then Bohr came, and then he gave the idea that only some specific orbits are allowed where electron can evolve, so they will not lose energy. And then he explained the hydrogen spectra as well. So then we have an idea that light, it has some dual character. It can behave like a wave, or it can behave like a particle also. In 1924, de Broglie came with this hypothesis that it's not only for light, some these subatomic particles with some certain circumstance, they can behave also like a wave, and give a very important relationship between the nature of particle and wave, that is lambda is equal to h by p, which is the Planck's constant here. So let me give an example here. So if you consider an electron, it's moving with a certain velocity. Now, if you calculate the de Broglie wavelength, it comes order of 10 to the minus 10, which is, it's like it's a gap between two atoms in a crystal. So that is why actually we see diffraction effect. But if you consider a macroscopic object, for example, a ball moving with some velocity, and we calculate the de Broglie wavelength, it comes to order 10 to minus 34, which is very, very small or negligible. That is why we don't bother about its wave nature. So now in 1925 and 1926, around that time, three scientists, Heisenberg, Born, and Schrödinger, they gave birth of the modern quantum mechanics. So introduced this matrix mechanics, then a mathematical formalism given by Born, probability interpretation, and of course the wave mechanics, the Schrödinger equation. So they basically, give a new direction to understand this microscopic world. Okay, so now let me start with a very simple system, which is harmonic oscillator system. And quantum mechanically, we know that now the energy is quantized. Okay, so this is the potential. So energy levels are equidistant. And this is the ground state wave function. It looks like Gaussian here. And these are the had excited states. So using this ladder operator, now one can get these wave functions. Now we know that wave function, it is a mathematical entity. So physical entity means we have to find the probability density. Here it shows the individual probability density of those wave functions. Now what about the particle? So this is basically a plane wave, okay, sine or cos term. So it's running from minus infinity to plus infinity. So it cannot carry the information. For that, we need to superpose these waves, and we can have a localized one, and that is the wave packet. Now, if we want to define a particle in quantum domain, so this way one can superpose quantum states and can get this kind of wave packet where, see, this is actually the probability of finding that particle in this region is maximum, and other places it is almost zero. So if we want to localize the particle, then we have to superpose n number of waves. Okay, so the momentum uncertainty will increase. And here comes the idea of the Heisenberg's uncertainty principle. So we cannot measure with accurately this delta x and delta b at the same time. Now, this is the general expression of a wave packet. It's a time-dependent wave packet where n number of wave functions one can superpose, and this is the weighting factor and this is a phase term. So this weighting factor is very, very important when we construct the wave packet. Depending on that, we can see different kind of wave packet, and we can see the long time evolution also. So here I have taken a very simple example, which is a Gaussian distribution, where from here we can see the individual contribution of these wave functions. So if we go beyond this number 25, you see the contribution is almost zero. So this number of wave function can superpose to create a localized wave packet. So as this is equidistant energy level we have seen for oscillator system, so energy is linear here. And suppose this is a constant term. So if we use this energy function in this phase, so one can have this time-dependent wave packet. And if you see the system dynamics, then at particular time, when t will be 2 pi by alpha, the phase term becomes 1. And it will behave like an initial wave packet. So that actually, it was studied with the Rydberg wave packet, and we found that for a long time, this when it has, initially it will behave like a classical particle. So we named the time scale as a TCL or classical period. And this is the definition of revival. So if it is coming back to its initial state after certain time, then we are saying that it is reviving after their revival time. So that time Schrödinger described this non-spreading wave packet of harmonic oscillator. He tried to find the the transition between quantum to classical, and then he described the coherent state. Later, Glauber, he actually give the definition of coherent state in quantum optics and give the mathematical formalism, and he got the Nobel Prize in 2005. Okay, so this is harmonic oscillator coherent state. Here you can see this behaving like a particle. There is no dephasing or decaying. It's moving intact, and it's coming back after their revival time. So if one can see the trajectory also in X and T, it's kind of oscillation only. But for the anharmonic system, it's completely different. So they basically show some interesting phenomena. It's not okay, fine. So see, the initially it was moving like a particle, wave packet will not dephase, but then dephasing started, and then very interestingly, it's breaking into mini wave packets. Okay, small wave packets. Three number 4 wave or 5 wave breakups can be seen, and finally it will regain the initial state at revival time. And if you see the trajectory, xt space, you will see very interesting, nice picture, which is known as quantum carpet in the literature. So that's the thing. It happened between when the time is rational fraction of t revival, the initial wave packet splits into mini wave packets, and that is called the fraction revival. Okay, so here actually mathematically one can write if the energy, it has also quadratic dependence, it has non-linear term, then there will be some extra phase. And when the time will be 2 pi by beta, beta is another constant, so the initial wave packet behaves like classically, then it will have only the linear dependence. For example, vibrating dieting molecule, it has same kind of energy expression. So one can see the system dynamics. For other system, if it doesn't have this kind of dependence, then one can expand it in Taylor series and can find this linear and quadratic term as well, and can find this 2 time scales, TCL or T revival, and finally can write the wave packet in terms of these 2 time scale. I can see the system dynamics. So when time is rational fraction of T revival time, we describe this as a fraction revival, and the initial wave packet splits. For example, if time is 1/4 of T revival time, then one can easily find from this expression that the initial wave packet, at this time will split into 2 wave packets. If at one third of T revival time, it will split into 3 wave packets. So that part one can check easily from this equation. So it looks very similar to this 2 wave breakup. It's like a superposition states. It looks like the Schrodinger cat-like state. So it has, this is very important state in a many application in different domain. So it was, there's this famous story about this, cat with this cat thought experiment was done by Schrodinger, and this name came from there. So basically, they put a cat inside a box and put some radioactive substance. So if it decays, then there was some poison. It will come out and it will kill that cat. If not, then the cat is alive. So if you don't open the box, you cannot say it's dead or alive, and it's kind of in a superposition state. So it's very similar to like this when we deal with the coherent state, and it will break into 2 parts. So one can compare with the live cat and dead cat, and in between one can have this quantum interference phenomena in phase space. So it's a very important state because I'm going to study here this Schrodinger cat-like state. And also another state is very important, which is known as compass-like state. Coordinate states, north, south, east, and west, it is situated here. And the individual, this pair can be considered as Schrodinger state. So one can see there will be some quantum interference in between. And if you take the diagonal pairs, even these two interference structure will overlap, and one can have very small regions, and which is very important because it has dimension below Planck scale. So we actually studied for a physical system, for postdoctoral kind of system, and got this kind of structure at fraction revival time. And this is another work for molecular system, this is for iodine molecule. Okay, so I'll explain those. Now, quantum parameter estimation, it's very difficult to measure quantum parameters with a very high precision. And, for that, if we repeat the experiment in number of times, then one can minimize the error and can take an average over there. Then the error scale says 1 by root n, which is the standard quantum limit. And so this is the ultimate limit one can have using the classical protocols. Now to beat this limit, one can use some quantum properties. And if you use this quantum superposition, entanglement, all those, then routine time enhancement is possible. And that is the Heisenberg limit. So this is basically the field quantum sensing domain is working to get this limit. And here this sub-Planck scale structures plays a very crucial role. Its dimension is below Planck scale, and it of course not violating the Heisenberg's uncertainty principle. Now, it was first mentioned in a paper by W.H. Judek in 2001 that he showed that this dimension, sub-Planck dimension is h bar square by total phase space support. So for the oscillator system, he explained that if, other system as well, if we have this kind of state, then one can find the sub-Planck dimension structures in phase space, and these are physically significant. So because of this principle, we have an idea that there should not be anything below the Planck scale, and if it exists also, they do not matter. But that common assumption is false. It is physically significant, even if you have any kind of perturbation or any kind of disturbance coupling with the environment. So this smallest structure you can detect first, and for any kind of measurement process also, it will disturb the system, and there will be very small shift, which is order of this or sub-Planck order. Then also it will make these two systems distinguishable because the other one becomes orthogonal. So that way it is very, very useful. And it, of course, plays very crucial role in Heisenberg limited measurement. Now, how to produce these structures in physical systems? So this is physically for the dieting molecule. We have considered the vibrational motion, and we showed that using this fraction revival phenomena, one can find the sub-Planck scale structures. So for that, we have taken the Morse system, which is a very well-known system. And we have taken these HA molecules. These are the wave functions and parameter values. And it has a finite number of bound states. So the dynamical symmetry group is SU2, and these are the corresponding generators. So using that, we have calculated this displacement operator coordinate state. And this is the time-dependent coordinate state. And this weighting factor, it comes from here. So it's very important because it decides actually the distribution. And this is the expression of energy. One can see there are, m is the vibrational quantum number. So there are linear and quadratic term as well. So from there, one can get this time scale TCL and TDVL. So if you see the system dynamics, then, okay, so this is first, let me tell you that, this is the distribution we have plotted. It shows that which are the level, vibrational level will contribute to create the initial wave packet. That is very, very important. If you change these, the coherence parameter, then it can change the distribution also. So here actually you can see when alpha is small, the vibration, the higher excited levels are contributing. When alpha is large, lower levels starts contributing. So depending on that, one can start with different kind of wave packet and can see the system dynamics. So we studied for two different cases. Here actually I'll show one. So this is the coordinate representation, and I have taken some snapshot. Okay, initial one is this is time t equal to 0. This is the coordinate state. Now 1/4 of t revival time, at 1/4 of t revival time, at this fraction revival time, it it's split it into two wave packets, but it's not symmetric as the potential anomalisity effect is there. And this is at half of t revival time. It is reviving, but with an extra phase. And this one is showing at 1/8 of t revival time, where it should split up into 4 wave packets, but it's not clear exactly what is happening here. So we move to phase, and they use the Wigner distribution function, where these are the contour plots. So this is the initial wave packet, and see it's the cat states, it's a cat-like states. So in between, one can see these interference regions, these negative and positive ripples. And here, interestingly, this is the 4-wave breakup. as we have taken lower levels of the molecular system, so this phase-phase support is small, so it's very closely spaced. But okay, there are 4 wave packets, and in between at the center, not very clear, this checkerboard pattern structure comes up, but it's a spotty kind of, small regions are there, which are basically the sub-Planck cell structures that we also checked here. So for alpha is equal to 1.4 and 2.5, these 2 cases, we checked in atomic unit is diminishing is skewing below Planck scale. So this is the first observation we did for the diatom molecular system. Now question is, so far what we did, it is for completely isolated system. But what will happen when there is a difference? So decoherence is, something it always try to destroy the quantum properties, right? And it's very difficult to isolate the quantum system. So here, this for vibrating molecule, there can be different kind of sources. There can be coupling with the rotational degrees of freedom, or coupling with the photonic or phononic degrees of freedom. And the environment actually we modeled with a set of harmonic oscillator, and we solved the Markovian master equation. So I'm not going here the mathematical part here, just showing that how it is affecting. Okay, this is for oscillator system, as it's a very well localized. So I started with that. And here one can see very easily, because of the coupling, these central interference regions, these are disappearing very quickly compared to the other interference parts. Whereas the coherent states are almost intact. So if the coupling strength is very small, then the small structures, they can detect fast, and then that will disappear. It will lose the coherence property. For molecular system as well, we can see this is for compass-like state, that is at fraction revival time when I have taken 1/8 of t revival time. Here, the first one, there is no decoherence, and the second picture shows there is a small coupling, and the third one is showing when the decoherence is large. So the central region is going to decay here. So that is what actually we studied with presence of decoherence in diatom molecular system. It's not very trivial to do because it needs huge numerical task also. And this is for for longer time evolution. Suppose if we wait for the longer time, obviously the system environment coupling will be strong, and the effect will be very prominent. So this is at 3/8 of T revival time. We see the central region, it's becoming going to vanish, and 5/8 of T revival time, it is almost vanishes. So interesting results we got for we studied it for diatom molecule in presence of decoherence. Now, how one can improve the sensitivity limit? So here actually we use a current control method. There is a lab in Japan, Professor Group. They have been working with the iodine molecule, and they experimentally actually visualize these quantum interference structures. And there are several papers also. This is one of the paper where they experimentally designed the quantum carpet. So it's very interesting result where they have used wave packet interferometry. And so we actually use this wave packet interferometry here. What we did using 2 optical pulses, one can create 2 wave packets. One packet which is having the only even number of eigenstates, another one is having odd number of eigenstates. And there is a relationship between the 2 wave packets. These phases are locked, and one can change the phase between the optical pulses, and that will be imprinted to the corresponding quantum wave packets. So using that mechanism, we have created a initial wave packet where changing the theta parameter, one can change their quantum interference structures. So this is the probability density. We have seen that how individual parts, even parts or odd parts are contributing. Here one can see when theta is equal to 0, only the even parts will contribute. When theta is equal to pi, only the odd part will contribute. When theta is equal to pi by 2, both even and odd are equally contributing. So here one can see that how they are affecting each other. So mainly we focus here at time 1/8 of T revival and 1/16 of T revival time. Because we know at 1/8 of T revival time, we can get this compass-like state. And it's very interesting at this time, if we have a control over quantum interference, then what will happen? And 1/16 of T revival time, there will be some kind of combination of two compass-like states. So it's also interesting to study. So we move into phase and see when theta is equal to 0, the initial state looks like Schrodinger cat state. It's Schrodinger cat state. Only the odd part is contributing here. Now, if you change theta is equal to pi by 4, so then even part starts contributing. And here, when theta is equal to pi by 2, both even and odd parts are contributing. And when theta is equal to pi, only the odd part, this Schrodinger cat, it is localized in momentum space. So interestingly, at particular time, changing this parameter, one can have a control over the quantum interference structures. This is at 1/16 of T revival time. So initial state when theta is equal to 0, say it's a like rotated compass-like state, the initial one, and then the theta is equal to pi by 4 or theta is equal to pi by 2, one can have this kind of interference region and the state looks like that. When theta is equal to pi, it looks like the original compass state, okay, and so we studied the sensitivity, okay, of these quantum interference regions and calculated here for different values of theta at 1/8 of T revival time. We found that when theta is equal to pi by 2, it gives the maximum sensitive region. And when theta is equal to 1/16 of T revival, this is the most sensitive structure one can have. And these are the corresponding states. So fine, so we see that using this quantum interferometry, one can enhance the sensitivity limit also in in this system dynamics. Now, enhancement is also possible if we consider the rotational effect that we actually, so far we have considered only the vibrational motion. Now we consider the rotational effect also. So for that, we have taken a rotating mode system. It's a one-dimension potential where it has both contribution. It's for vibrational motion, and this is coming from the rotational part. So if centrifugal force is high, J is high, then obviously, the internuclear distance will change and the potential will increase. So here we have studied for iodine molecule, and the initial wave packet we have created, which is peaked around the level 10, and we see the system dynamics at particular time, 1/4 of T revival time. You see, if we change the value J, initially it is 0. The blue line is showing when the J value is 0, it's only the vibrational wave packet. At 1/4 of T revival time, there will be two-way breakup. Now, if we change the coupling, J is equal to 45, then dashed line is showing that these two wave packets are coming closer. And when J is equal to 65, one can see some kind of ripples are captured in this coordinate representation. So changing this, this coupling or this effect of rotational, one can see that will change the vibrational dynamics. So here actually we calculated the sub-Planck scale dimension for cat states with different values of J. So we see it's a kind of oscillatory behavior it shows, and all the values are coming below Planck scale. And among them, when J equal to 0, the initial one, this is the corresponding state, cat state, and J is equal to 38. Around that time, we found the minimum, sub-Planck dimension. This is for cat state. For compass state as well, one can check. So it looks like that when J equal to 0, it's look like this compass-like state, but the minimum sensitivity comes when J is equal to 64. This is the second picture. One can see it's a kind of rotated compass state. So very interestingly, one can see the same thing we also got when we consider the wave packet interferometry, and we got the maximum sensitive structure as well there. So it shows the enhancement of sensitivity when we consider the rotational effect. Okay, so now so far we have been discussing about the quantum superposition. So another important thing is the quantum entanglement. So is there any role if we consider this quantum entanglement? What will happen there? Can we enhance the sensitivity limit? So we studied this for another system, that is the cavity QD. And it's a very well-known system because a lot of work already done. And in 2012, Professor Harris and Weinland, they got the Nobel Prize because of their groundbreaking work. So they basically did the experiment where these Schrodinger cat-like state experimentally realized in their lab. So this is the setup where they can, trap, the field is there and inside the cavity and send some atoms through that, where there will be some atom field interaction. And finally, when they observe the atomic state, then one can find the field, in Schrodinger cat-like state. So this is the schematic diagram. And these R1 and R2, these are Ramsey interferometers. So this is, of course, is one of the appropriate system to realize this kind of quantum phenomena. And already, as I mentioned, that Schrodinger cat-like state is observed in their lab. So as we studied that compass state is also very important because it shows this sub-Planck dimension, and it has very good application in quantum sensing domain. So this idea actually first introduced by Professor Panigrai in 2008, that if we use two entangled cat state, then one can get these small sub-Planck dimension structures. So entanglement can be used there to get the compass state. So our idea is to design, to give a model, experimental model, which can be done in Haroch's lab. So in this case, we use two cavities and three atoms are required. So these two cavities, there will be two coherent states, and we send the atom through this one by one. So first atom, it interacts with the field with the cavity 1, and then it also interacts with the cavity 2. Then atom B, it goes through, where we switch off the cavity 2, it only interacts with the cavity 1. And the third atom, which interact with cavity 2, and we switch off the cavity 1. So if we then measure the final state of atom, then we can see the field states. And this is a total, complete, cavity QD circuit. One can see what are the, phases are introduced with this Ramsey interferometer. So it's very important, tricky way to give, the output should be two cat states. The field state should be in a cat state, and there should be some entanglement between these two field. So this is the total diagram. An idea is that field 1 or field 2, it will be like this, and two cat states should be entangled. So at the middle, we can have the smallest structure, which are the sub-Planck scale structures. So here actually I'm not showing all the states, the final possible states. If one do the measurement on the atom, then one can have these 8 combinations, 8 types of field states. And among them also we found that these 4 states are maximally entangled states. So this basically, it looks like the bell-like states. So these are very important to study. And one can have this kind of entanglement between two cat states. So if we see the phase representation, there for the first state we have just shown here. For field 1, this is the phase space where one can have these entangled cat states, and the central region, we zoomed this region where one can see very small tiles, small structures, which are the sub-Planck structures. And for phase 2 also, we have plotted similar kind of structure one can have. So one can study with that, and this is a proposal that experiment can be done in their lab, and then it has very a nice application in quantum domain. Okay, so now this is what will happen if we add photon. So already we talked about the coherent state. So photon added coherent state, it's very important. It was introduced by Professor Agarwal and Tara in 1991. Coherent state is the most classical object in quantum domain. So this, if we add a single photon, it starts showing its non-classical properties. For example, this squeezing or subcontinuum statistics. So it's very interesting to study because see, this is a coherent state in phase space. So if one photon is added there, one can see the squeezing property, and it shows also the negativity in Wigner function. So it's in literature there are many works in this direction, and the first experiment, it was done in 2004 by this group, where they experimentally realized this single photon added coherent state. So what will happen if we add a single photon to a cat state? So this is the cat state where no photons are added, but the second picture is showing when one photon is added there. So as a whole, we cannot see, it looks almost similar. But if we see the central region where the dimension is very small, level of the Planck dimension. So here one can see that single photon addition can change the fringe. The red one will shift it to the blue one. So negative region, one ripples will be shifted. So this idea also, it was given Professor Panigrahi in 2021 that, this photon addition, if we add in a cat or compass-like state, so that can, can be very useful. It can be act as a detector, and it will have very good application in quantum sensing domain. So we studied for molecular system. So here actually this is for the iodine molecule, and these are the corresponding eigenfunctions and energy expressions are given. So one can of course find the photon added coherent state. So our number of photons are added here, and finally this is the coherent state, photon added coherent state. And the corresponding this distribution, we got this, it looked like that. So it's quite a big expression, and the corresponding distribution function, if we change the value of R, that means if we change the photon number, how many photons are adding there, then it will change the distribution function. So depending on that, see when R is 0, its lower levels are contributing. And when R is increasing, then it's moving towards the higher levels. And the corresponding initial wave packet is shown here. So if you see the system dynamics, at particular time, we have just taken here at time 1/4 of T revival time. See the cat state, the two-way breakup. With this addition of photon, they are going far apart. When red line is showing when R is equal to 4 photons are added, this blue line is showing when 2 photons are added. So one can see that they are going far apart. And this is also at 1/8 of T revival time. These two wave packets, and in between, these are the quantum interference regions. So here also one can see the shift of these small regions. So for that, we also calculated the Mendel Q parameter. And as we know that for non-classical states, it should be below 0. The value, as this is for cat state, already the value started with the minus 1, almost minus 1, 0.1. And then, it's with the addition of the photon, the value is going down, and it's going to saturate at the value of -1. So this basically shows it's the non-classicality is increasing. Now it is again the Wigner distribution function, and for photon added CAT state, and here one can see that these two coordinate state, and these are the interference regions, and with the increasing of photons, these ripples are becoming finer. So this sensitivity is increasing. Also for compass-like state, so here actually at the central region, there are 4 coordinate states. It's quite well distinct even in the molecular system, because now we have taken ideal molecule, and for that this phase-phase support we have chosen such a way, the distribution such a way that we can have this well distinct wave packet. So these are the 4 wave packets, and one can see this quantum interference region at the middle, and the central region, one can find this similar kind of checkerboard pattern here also, but not symmetric. And with increasing photon numbers, this as a whole, the phase-phase support is increasing, and when one can see that the dimension is decreasing, these these structures. And this is the variation. I mean, we check the quantum sensitivity for CAT state and compass state with the photon addition. So if we increase number of photons, see for the CAT states, the sensitivity will increase. Similarly, for the compass state also, the sensitivity it is also increasing. So this is recent work we have done it, and further also we are working with the photon subtraction addition. When we do it together, what will happen in quantum sensing domain. So today I'll conclude here. So we actually studied that this quantum precision measurement, which is very it's a very challenging task to it's to measure the quantum parameters with a very high precision, and sub-Planck structures, it plays a very important role there. And also we first time showed that in diatom molecule, where we consider only the vibrational motion, that it plays, one can have this sub-Planck structure there at fraction revival time. And in presence of decoherence also, we showed its sensitivity. And then we showed that coherent control method can enhance the sensitivity limit. Also using rotational amendment, we showed that this one can get finer precision also. And then we have shown for another system using the cavity QED, one can use the property of entanglement, where entangled CAT states can be found, and that will give a compass-like state. And one can have again the sub-Planck scale structure, which having the Heisenberg limited sensitivity. So that's very important to study. And then finally, I discussed about the photon added coordinate state in molecular system, and which showed, very interesting result where the sensing is, precision is increasing. Okay, thank you very much.
Thank you very much, ma'am, and really enjoyed your exploration of sub-Planck structures.
Thank you.
And the best part of the talk, which I liked, was that you gave very interesting models for exploring these ideas. You started with very fundamental things: harmonic oscillator and harmonic oscillator, diatomic molecule, and rotating Morse system, and cavity QED. Yes. And I think it was very enlightening, at least for me, because I heard this for the first time. I have really enjoyed it.
Okay,
and
thank you.
As I was listening, there was one question which was coming to my mind.
Yes,
pardon my ignorance, and that was regarding the choice of phase-space Wigner distribution. And what does it bring new than the traditional phase-space distributions which are used, say, in statistical mechanics? Is the question clear?
Yeah. Actually, So here actually we are dealing with quantum phase space where and different kind of probability distribution one can study there. So here we are studying the Wigner distribution where one can see the negative region as well. So in this case, of course, in quantum domain again we have this fundamental limit it should follow, that is the Heisenberg uncertainty limit. So total as a whole, the system, if you see, if we calculate here, that is of course satisfying the Heisenberg uncertainty principle. But this is a part of a system, this quantum interference region, which dimension is coming below the Planck scale. So that shows the negative regions, and it basically gives a signature of non-classicality.
Okay, thank you very much. So, dear participants, the talk is open for questions, and we have about say 7-8 minutes. You are most welcome to switch on your mic or raise your hand and ask question.
Can I ask a question?
Yes,
Usha
please,
Devi.
go ahead.
So,
yes,
very interesting talk. I have two questions.
Thank you.
So,
Yes.
first one is to ask you, you have taken Wigner distribution function and done the sub-Planck structures and explored all that. But I wondered, there are different operator orderings of, let us say, Q and P, from classical to quantum, whenever one constructs a phase-space distribution. So if it were, let us say, Husimi function or some P function, the structures, would they differ? Because it's the operator ordering which matters than the wave function. So I just wondered if there is any difference in such phase-space functions where only operator ordering is different. That is my first question.
Yeah, I mean, exactly.
Say, for example, P function, Q function, and the Wigner function.
Yeah, for Q function will not have the evidence of negative regions there.
No,
So,
I am asking about the sub-Planck structure, like how you have checked it. They may be different is what I believe.
Yeah, for our case, actually, we studied only the Wigner function because, yeah. So one may, of course, can study different kind of distribution. So as we are interested in these negative and positive ripples, this sub-Planck dimension, so that is what actually we have studied to explore all this property of Wigner function. Yeah, of course, one can study and can see what will happen there. So that can be done.
Second question is, you have focused on cat states, but there is analogy between continuous variable cat states and what is a spin state. That is, if I connect it with the angular momentum, so of spin j, so this is something like a j plus j minus j kind of a state. So am I clear here? That is, it is a spin j and minus j combination will give you a noon state. So now I just wondered, suppose you had tried to generate other Dickey states, not just the noon state. So they may also be interesting because noon states always have their difficulties. So such attempts are done anywhere?
Yeah, actually, in this system, I have discussed about mainly these Schrodinger-like states and compass-like states. But one can, of course, see other combination because I have not included other works also here. For poststellar kind of potential, we studied benzene-like state, which is the superposition of 6 wave packets. So that also we found there also one can find the sub-Planck dimension. Even not only that, we have another paper also where we can consider n number of wave packets. We can increase the number of wave packets and can see what will happen, in the quantum interference region. So these are other actually observation one can of course use. Here actually I mainly focus on these two states to see that how one can enhance the sensitivity to make it a simple actually. But of course, yeah, in other cases one can study other combination also.
Thank you.
Okay.
Yes, Suranjana, I have one.
Yes, yes.
Yeah, please.
Yeah. See, I mean, Rydberg atom is the place where, originally this wave packet revival,
Yes, yes.
sub-Planck structure came. And anybody looked at, this finding sub-Planck kind of structures in Rydberg wave packet as well?
In my knowledge so far, I don't think that it is not done yet. Yeah, because it's a kind of three-dimensional scenario comes into there. So if we go into the phase, then we have to consider six-dimensional phase. So that's a bit complicated. So, but of course, one can study also, and it's very interesting to see because this wave packet dynamics started with that idea only with this Rydberg atomic states. So there are several papers and they seal. So I forgot to mention this movie what I have shown here. That is a for Rydberg wave packet, and several papers are there. So yeah, that can be done, but it will not very trivial actually.
Yeah. Yeah, I just wanted to add because Professor Valvale asked about
Okay.
why Wigner function. Because actually this, after Rydberg wave packet dynamics was proved in mid-80s, 1984 85, it was actually Wheeler, Feynman supervisor, who brought in the concept of interference in phase space. So this interference, what we are seeing, is actually due to Wheeler and slide. And if I remember, Jay's contemporary physics article has Q function plots, right? Q function plot, like Usha was asking. I think he has, but it's keeping in mind P function, what happens. Yeah.
Yes.
So, are there any more questions, please?
Yes, I have two questions, quick
Please,
questions.
Please, quick question. We have just 2 minutes.
Okay, thank you for a very interesting and informative talk. So, in quantum optics, one can apply quantum homodyne tomography to see the changes in interference pattern before and after sensing. And this tomography mechanism requires a huge number of optical tomograms and they are very intensive. So my question is, what kind of measurement mechanisms do you propose?
Yeah, for a molecular system also one can do, it is known in the literature, one can do emission tomography. So basically they have to then reconstruct the Wigner function from there. So that way they can find the total information of the vibrational states.
Okay. And second question, what kind of physical mechanism is required to bring two cat states? I mean, you have shown us these perpendicular to each other to entangle them and they become compass-like state. So any mechanism, physical?
Yeah, actually, for example, in cavity QED system, I have already shown that they have to do the measurement on atoms, and the field will be in this. They will be entangled, and then one can find this compass-like state. And for other cases as well, for when we see the time evolution of the wave packet, we see the wave packet dynamics when we considering the molecular system, then it's automatically in the system dynamics we are finding this compass like state at 1/8 fraction interval time, so we don't need the entanglement separately there, so that comes in their time evolution itself.
Thank you.